So in this talk, I'm going to talk about some recent structural lemmas for depth-2 structural circuits. And hopefully, I will talk about some potential approach to prove lower bounds for depth-2 structural circuits. So, okay, first, some definitions. Ryan already covered them, so I'll just go through them quickly. So structural gate is just a function of an indicator of the intersection of a Boolean cube and a half space. So it's just whether w dot x is bigger than t. So w here will be a integer vector, and t will be an integer. And for the majority gates, it's a special case where they are both bounded by a polynomial. So structure of structure is just a top structural function composed with many structural functions at the bottom layer. And similarly, we can define structure of majority, majority of threshold, and the majority of majorities. So some histories. Exponential lower bounds are known for all these special classes, for majority of majority, for majority of threshold, and for threshold of majority. Actually, these two classes are equivalent. But for threshold of threshold, we know very little. So we don't even know whether nx, the non-deterministic exponential time, is contained in the threshold of threshold polynomial size. So in this talk, when there's no thing before the class, I will assume that they are of polynomial size. So in this talk, I'm going to talk about some potential approaches for resolving this open question. Ryan Williams has an algorithmic approach to lower bounds. So basically, say something like lower bounds for C will arrive by designing some non-trivial algorithms for C. That's actually some subtlety here, because in the usual way of thinking about this, there will be some depth increase. But we are thinking about fixed depth circuits like structure of threshold. But it turns out we can make use of some structure of structural gates to get rid of the depth increase here. So the natural question is, how hard is the algorithmic analysis of structural circuits? So for example, how does it compare to structure of majority or majority of majority circuits? In this work, I will show actually from the perspective of designing algorithm for them, they are equally hard or easy. This is quite counterintuitive because we know that exponential separation between them as the computational model themselves. So what's the algorithm question we are interested in? The first one is the most basic question we all love, the C-set question. So we are given a circuit, and we ask whether there's an input which makes this circuit satisfiable. And the second question is CAPP. So it's basically just a derandomization question. So we are given a circuit, and we want to estimate the acceptance probability when it's given a random input with some additive error, epsilon. So now we define what is non-trivial algorithms. For non-trivial set, we want to shape a super polynomial factor from the trivial 2 to the n brute force algorithm. And for the non-trivial CAPP, we want to also shape this super polynomial factor. But we also want the arrow to be something like holds for every inverse polynomial function. This is useful for some later technical derivation that I will show you in the later slides. So let's talk about our first result. So the first result is polynomial size threshold of threshold and the threshold majority are equivalent for non-trivial set algorithms. So what does this mean? So if we have an algorithm can shape a super polynomial factor from a threshold of majority set algorithm, then we can get similar algorithm for threshold of threshold. The second result is polynomial size threshold of threshold and the majority of majority are equivalent for non-trivial CAPP algorithms. So if we can derandomize majority of majority, which seems much simpler because we know exponential lower bound, even slightly just save a super polynomial factor, and this will get us some some non-trivial CAPP algorithm for threshold of threshold. And this will get us the lower bound we want. Okay, so first I want to talk about why we need the new structure lemma as in the topic. So anyway, we want to connect the threshold of threshold and majority of majority to make use of the algorithm for this class. So we know that's a very old result, actually older than me. So it shows something like threshold of threshold is in depth 3 majority of majority of majority circuits. But the question here is we only have majority of majority SAT, and the depth actually is increased. And we of course we don't know how to make use of the depth 2 case to solve depth 3 case. So we cannot rely on this old structure lemma here. But what if we had a top OR gate? So imagine this gate is now an OR, so these people will be happy. So because suppose we have an algorithm for C set, then automatically it implies an algorithm for OR of C set, right? Because you can just enumerate all these subcircuits and apply the set algorithm for each of them. And since we have a non-trivial saving of super polynomial, a polynomial fan-in here is okay. And also, what if we have a disjoint OR top gate? A disjoint OR is just something, it's a promise OR gate, which at most one input is ever true. This is actually even better. Look at, he's very happy. So because in a CAPP algorithm, want to estimate the probability of accept a random input, but disjoint OR is just a sum. So you can just sum them up. Just try each subcircuit and sum the probability up. And this is why we want the epsilon to be 1 over polynomial for every polynomial, because then the fan-in here may introduce some error.
Okay. How do you end the OR? How do you end the OR of C?
What?
The previous slide, how do you end the OR? How do you end? Why does it help you that it's an OR?
I'm going to talk about, you mean how to write this?
For SAT, not for CAPP. Okay. For SAT.
Yeah, for SAT. So for CAPP, we have to disjoin OR because it's a sum.
Now the fan-in of that OR can be almost exponential, right?
Yeah, but I think
or 2 to the whatever the same.
depends on the algorithm, I think, because the definition here, non-trivial means only save a super polynomial factor.
Oh, okay.
Yeah, but yes, I think it has some connection with other algorithms if we relax the definition here. Yes, actually, I will talk about this later. Yeah. Okay, so this is our first structure lemma. So a threshold of threshold gate, a circuit, can be explicitly written, which means that an algorithm can construct this decomposition as an OR of polynomial in many threshold of majority circuits. So as a trivial corollary, we'll have if we can shape a super polynomial factor from the set algorithm for threshold of majority, as will automatically imply a similar algorithm for threshold of threshold. So this is good. Okay, structure lemma 2 is more complicated. So I have to read them carefully. So for a parameter epsilon, we show for every threshold circuit of size S with n inputs can be explicitly written as a disjoint OR of majority circuits, such that the top gate has a 2 to the epsilon n fan-in, and all majority subcircuits have size S to 1 over epsilon. So here are 2 concrete settings. So when we set epsilon to be an arbitrarily small constant, then we can write threshold as a sub-exponential or disjoint OR of majority. And if we set epsilon to be much smaller, then we can write threshold as a polynomial disjoint OR of sub-exponential size, majority. And this can also be applied to the when the bottom function is a end. So we can show something like for all epsilon, every threshold of end function of this size and inputs can be written as a disjoint OR of majority of end circuits. So this is actually just a polynomial threshold function of degree k. And the parameters are similar. So the corollary is PTF of degree k with arbitrary weights can be written as a sub-exponential disjoint OR of PTF with polynomial weights, but with degree 2k. Here we have some constraint on the fan-in, but here it's okay because we don't have constraint here. They're there. So the first open question I want to ask is, can we strengthen this lemma from threshold of majority to majority of majority? So can we show threshold of threshold? Can we write a threshold of threshold as an OR of polynomially many majority of majority? This will show they are equivalent for non-trivial set algorithms. I can only show something less interesting. I can show a non-trivial sharp set algorithm for majority of majority will imply a non-trivial, non-deterministic unset algorithm for threshold of threshold. It seems very absurd, but this is already enough for NX is not in threshold of threshold. So I want to strengthen this sharp set to just set. Then this will be interesting. So this is I'm going to talk about why we can get rid of the depth increase issue, because in the best optimized version of the lower bound by algorithm implicit theorem, we actually need a set algorithm for N3 of C, but not just C. But we want to get implication for threshold of threshold themselves. So we cannot really have this +1 increase in the depth, which is cause us some problem. And actually, we don't know whether N3 of threshold belongs to threshold of threshold. Actually, maybe not. So we have to deal with them. So we need some help from the exact threshold gates, which is a close relative of threshold gates. So now the definition is slightly changed. The exact threshold gate is an indicator function of w.x equals t, but not smaller than t. There are some structural results for connecting these two types of gates. So the first one is a threshold gate can be written as a disjoint OR of polynomially many exact threshold gates. And the second one is exact threshold gates of threshold belongs to threshold of threshold. And second one, the third one is exact threshold is closed at the end. So now we can try to deal with this using the observation we discovered before. So first we have an N3 of threshold of threshold. Now we first write a threshold as a disjoint OR of exact threshold. Then we get this. Now a disjoint OR is actually just a sum, and then end is just a multiplication. So we can switch the order. Now it becomes disjoint OR of N3 of exact threshold of threshold. And now exact threshold is closed and taking an end. So it becomes disjoint OR of exact threshold of threshold. Finally, it becomes disjoint OR of threshold of threshold. And the good thing here is disjoint OR can preserve the CAPP algorithm and the set algorithm. So now we arrive at this. Non-trivial set algorithm or CAPP algorithm for threshold of threshold will imply the similar algorithms for N3 of threshold. And this will imply NX is not in threshold of threshold. Is that clear?
So does this answer Ryan's question? Ryan had a question about whether an algorithm for threshold of threshold implies some lower bounds.
Yeah, this was for evaluating a threshold on many inputs.
Yeah.
There's a reduction from that to set that includes the OR, which breaks this argument.
Okay, so you asked for sharp sum.
What's sharp set?
No,
It's different. Ryan is talking about evaluation problem. So it's like you are given a stretch of circuits. You want to know the output of this circuit on every input. And here we are talking about set algorithm, which is different.
So to go from one to the other, you would need the evaluation algorithm to work on unbounded Venn and ORs
of threshold. Yeah.
as opposed to bounded Venn and ANDs.
Exactly. In super polynomial or something like that, or something.
Yeah, the key point here we can make use of this is like it's only AND3. So switching these two is still polynomial. If it becomes like AND of a so polynomial, then everything will then work, I guess. So the corollary here is if we can solve majority CAPP, just save a super polynomial factor on running time from the brute force algorithm. And this would imply nx is not in stretch of threshold. And this problem seems simpler than the stretch of threshold case because we know there's an exponential lower bound for majority. So the real question here is, can we mine any non-trivial set or CAPP algorithms from the exponential lower bounds proofs for majority or threshold majority? And this, if we can do this, then this will imply nx is not in threshold and solve this open question. Yeah. So next, this question actually has connection to fine-grained complexity. So in this slide, I will show how can we can actually reduce the set algorithm set question for stretch of threshold to these natural questions in computational geometry. The technique is very standard. You just split the variables into two parts, and you enumerate all the assignments to each of the parts, and you do some reduction. So the first question is dichromatic closest pair. So you are given n points, which are either red or blue, in like polylog dimensional Euclidean space, and you want to find the closest pair. And the second question is you want to find the furthest pair. And the third question is you are given n points and then hyperplanes in polylog dimensional Euclidean space. And you ask, is some point on some hyperplane? If there's an algorithm which can shape all the logs from the trivial n squared time algorithm for these questions, then that would imply nx is not in threshold of threshold. Now the algorithm has to be deterministic. So this question seems to be has nothing to do with circuits, and they seem to be innocent computational geometry question which has been studied for many years. So probably you can make use some tools from computational geometry to at least shape some logs on them. Another question I want to talk about is a simple CAPP lookalike question. So you are given two sets A and B of d-dimensional Boolean vectors, and then integer t. You want to approximate if you choose a random pair from A times B, whether the probability that they are in the product is bigger than t, with some additive error epsilon. By reduction from majority CAPP to this question, you can show if this question you can generalize this and approximate the probability within inverse polylog error in n to the 2 over log 2 little 1 n time. Then this would imply nx is not in stretch of threshold. This seems to be a simple looking question, and I have been thinking about this, whether we can show some better generalization algorithm for this, and that will lead to the lower bound we want. So the final open question is, can we slightly improve the complexity of these problems or show why they are so unlikely? And if we succeed in this, this would show nx is not in threshold of threshold. And finally, I want to talk about another interesting connection, which is also discussed in this paper, but it's not about threshold, it's about general threshold circuits. So we know k set, the best running time is 2 to the n times 1 minus 1 over k. It hasn't been improved for many years. And also we know the general lower bound for general threshold circuits of unbounded depth is around n to 1 plus c2 minus d. So it's some constant here. So this lower bound will become linear when the depth is log n. Yeah. So actually, we don't know any non-trivial lower bound against the log n depth threshold circuits. It's even consistent with the current state of knowledge that e to the np has a threshold circuit of log n depth and on wires. So we can actually show something like if the algorithm for k set can be slightly improved to this. So originally it's 1 over k, but now if the dependence on k becomes slightly better, then this would imply e to the np has no on size log n depth threshold circuits. This is based on a reduction from threshold circuit set to k set in recent work. So now I want to conclude the talk and summarize the open questions. So first, we show some equivalence result for threshold, and its subclass from the algorithmic perspective. So these two classes are equivalent for non-trivial set algorithms, and this class are equivalent for non-trivial CAPP algorithms. And also we show non-trivial set algorithms for this class, and all non-trivial CAPP algorithms for this class would imply nx is not in threshold of threshold. And we get rid of the depth increase issue. And finally, we discussed that slightly improving the running time on geometry questions will imply nx is not in threshold of threshold. And we have 3 open questions. Since we still have some time, I actually want to discuss some another open question I was thinking about, but I don't know the answer. Maybe that just it's very simple, so it's maybe good to bring it up. So we know exponential lower bound against the threshold of majority. And by the previous discussion, we know if we have a top OR gate at the if we have a top OR gate, then this will make the set question equivalent. So I'm thinking about, can we show a lower bound on OR of 2 threshold of majority circuits? It seems like it should be very close to threshold of threshold, right? It's only an OR of 2 of them, but I don't know how to prove it. It seems maybe it's already known, but I thought about this for a while. It seems to me like probably this circuit already has a large sign rank, so we cannot use the sign rank method. But anyway, this seems very close to threshold of majority, so we should be able to prove some lower bound. I mean, superpolynomial lower bound. So this is the final open question I want to ask here. Yeah. Any questions?
Thank you. Questions?
If all your results are about depth 2 TC0 circuits, are there any prospects for depth 3 TC0 circuits beyond?
So actually, the equivalence result will for the equivalence here holds for all depths. So I can show for all constant depth d, the CAPP question for arbitrary weights and the polynomial weights are equivalent. This could be helpful for the further development of the finding CAPP algorithms. Yeah. But currently, I'm still thinking about threshold circuits that are very hard.
So, isn't this class R2 a threshold of majorities that's contained in, I think it's contained in threshold of degree 2 polynomial threshold functions? Something like that?
I'm not sure.
If you took XOR, it should be.
Yeah, so
You make it output -1 or 1 or
But
something.
why
if this is a
are the same?
parity XOR 2, then that's true, but I'm not sure for OR 2. Actually, that's a lower bound by Shestov that end 2 of threshold. This function has an exponential, has an very large, maybe root threshold degree. So end 2 of threshold seems, at least from the perspective of threshold degree, is already very hard.
Yeah, but okay, but I was saying instead of threshold degree, look at degree to polynomial threshold function.
Degree 2.
Oh, sorry.
That's what you're saying.
That's what you mean by threshold degree?
Yeah, threshold degree is just the threshold of n, right?
Oh, okay. Yeah.
So there's no nice distributive laws.
Okay.
This question is annoying because it seems very simple, right? But I don't know how to put a lower bound here.
I guess correlation bound is one apply.
The correlational bound only works for polynomial size. So I think Ryan proved a correlational bound for like n to 1.4 size of threshold majority, but the larger size is open. So I want to ask whether there's a polynomial, super polynomial lower bound for this class, and this seems open to me.
Can you go back a few slides?
Oh, sure.
Maybe 2. Okay, there's a good reason for. So can you tell us a good reason?
Oh, I forgot that. So yeah, sure. So I and Roy tells show something like suppose consider the BFE question. So it's the Boolean formula evaluation question. If we can show this is not in threshold circuits of n to 1 plus c over d for any c bigger than 1, then this will imply nc1 is not equal to tc0.
Circuits of depth D.
And depth d, yeah. So the d here means the depth. Oh, maybe I.
But that just says that there's a good reason that it might be hard for functions in NC1.
Yeah.
If you go beyond NC1.
Yeah, that's true, yeah.
More questions? Let's take Lijie. Let's thank you.